totient function. Euler's totient function is actually denoted as phi of n. What is this phi of n? This phi of n is the number of positive integers that are lesser than n that are relatively prime to n. I know it will be difficult for you to understand now, but this concept will be clear when we see some examples. Let's dive into the first example. Example number 1. Here we are going to find phi of 5. So here n is equal to 5. Let's solve this and understand what is this Euler's totient function phi of n. We know the n value which is given here is 5, right? So as per the definition, how many numbers that are less than n are relatively prime to n is phi of n, isn't it? So here n is equal to 5. So the numbers that are lesser than n are 1, 2, 3 and 4 because here n is 5. So numbers less than 5 are 1, 2, 3 and 4. So out of these numbers, how many numbers that are relatively prime to n? So we need to check, is 1 and 5 are relatively prime, 2 and 5 are relatively prime, 3 and 5 are relatively prime, and 4 and 5 are relatively prime. So we need to check how many numbers that are less than n, that is these numbers that are relatively prime to n. So that's what we are going to find. So as per the definition, we are taking only the number of positive integers that are lesser than n that are relatively prime to n. For example, if we are going to compute phi of 3, then we are going to focus on numbers that are less than 3, which are 1 and 2 only. We are ignoring 0, minus 1, minus 2, all negative numbers. They are also lesser than n, isn't it? Because the definition says we are going to focus on number of positive integers less than n are relatively prime to n. So it means obviously we are ignoring 0 and minus numbers or negative numbers. In the last presentation, we understood that when two numbers are said to be relatively prime. For that, I asked you to compute the GCD. For computing the GCD, I recommended you to use the Euclidean algorithm, right? Anyway, we are going to find the GCD. So I am going to compute the GCD and I am going to confirm whether it is relatively prime or not. So I am going to compute GCD of 1, 5, 2, 5, 3, 5 and 4, 5. So let's check it out. So GCD of 1, 5, GCD of 2, 5, GCD of 3, 5 and GCD of 4, 5. So we can see that GCD of 1, 5 is 1, 2, 5 is 1, 3, 5 is also 1 and 4, 5 is also 1. If you want to know how to compute the GCD using Euclid's algorithm, I request you to watch my previous lectures where I have computed GCD using two methods. You can pick and choose any one of the methods whichever is comfortable to you. Whenever the GCD of two numbers is 1, then that number is said to be a relatively prime number. In this case, 1 and 5 are relatively prime, 2 and 5 are also relatively prime, 3 and 5 are also relatively prime, and 4 and 5 also are relatively prime numbers. As per the definition, how many numbers that are less than n are relatively prime to n? 1, 2, 3, 4. So there are 4 numbers that are lesser than n that are relatively prime to n. So there are 4 numbers that are less than n are relatively prime to n. So the answer is phi of 5 is equal to 4. It means there are 4 numbers. What are these numbers? 1, 2, 3 and 4. All these 4 numbers are lesser than n, right? Yes, they are less than 5 and they are relatively prime to 5. So the answer for this question is phi of 5 is equal to 4. Let's see another example where you will get more idea about this. In this example, we are going to compute phi of 11. We know the given data n is equal to 11. So we are going to find how many numbers that are less than 11 are relatively prime to 11. So we know the numbers that are less than 11 are 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So we are going to find how many numbers in these 10 numbers that are relatively prime to 11. So we are going to obviously compute the GCD, right? So we are going to compute the GCD of 1, 11, 2, 11 up to 10, 11, right? So let's see that now. So we are going to compute the GCD of 1, 11, 2, 11, 3, 11, 4, 11, 5, 11, 6, 11, 7, 11, 8, 9 and 10, 11, right? Are 1 and 11 are relatively prime numbers? Yes. What about 2 and 11? Yes. When the GCD is 1, then they are relatively prime numbers. So in this example, we can see 3, 4, 5, 6, 7, 8, 9 and 10 are relatively prime numbers to 11. because the GCD is 1, isn't it? So in all the cases, the GCD is 1. So there are how many numbers that are relatively prime to 11? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 numbers that are relatively prime to 11. So it's clear that the answer for this question is phi of 11 is equal to 10. Now let's see the last example. Find phi of 8. So we are going to adopt the same methodology what we had followed in both the examples previously. So the solution goes like this. Here n is equal to 8. So we are going to list the numbers that are less than n, which is from 1 to 7. So we are going to compute the GCD, right? So GCD of 1, 8, 2, 8 up to 7, 8. Now in this case, if you see here, GCD of 1, 8, 1 is the answer, right? Whereas here GCD of 2, 8, 2 is the answer. GCD of 3, 8, 1 is the answer. GCD of 4, 8, we have 4 as the answer. When we compute GCD of 5, 8, we get 1 as the GCD. When we compute GCD of 6, 8, we get 2. When we compute GCD of 7, 8, we get 1 as the result. So how many numbers that are relatively prime we are going to check, right? So we have 7 numbers. Out of these 7 numbers, how many numbers that are relatively prime to 8? Let's check it out. Wherever GCD is 1, then they are relatively prime, right? So 1 is relatively prime to 8. 2 is not relatively prime to 8. 3 is relatively prime to 8. 4 is not relatively prime to 8. 5 is relatively prime to 8. 6 is not relatively prime to 8. And 7 is relatively prime to 8. Now, out of these 7 numbers, how many numbers are relatively prime to 8? 1, 2, 3, 4. So, there are 4 numbers that are relatively prime to 8. So, phi of 8 is equal to 4. I hope now you understood the concept of Euler's Totient function, which is also called as a phi function. Now, the big problem is, let's say I am asking you to compute phi of 1000. Is it possible to compute GCD of 1, 1000? GCD of 2, 1000, GCD of 3, 1000 up to GCD of 999, 1000. It may be possible, but think of the time it takes to do that. Is there any shortcut for doing this? Yes, that is what we are going to see in the next lecture. So computing the Euler's Totient function or phi function for smaller numbers, it will be easy. If the numbers are big, then we need to think of solving it in an easier manner. So keep the fingers crossed. In the next lecture, I will explain you how to compute the Euler's Totient function or phi function for bigger numbers using